Hello, welcome to this session on System Verilog for verification. Today I am going to discuss about one of the most powerful feature of System Verilog, that is classes. Classes plays a very important role in object-oriented verification methodologies like UVM. So let's get started. So this is what we are going to cover in this session. So we will start by understanding what SV classes are, followed by how objects are created and used. We will then explore constructor, object assignment, lifetime in class, and how static properties behave. Next, we will get into inheritance, method overriding, and also learn about the super keyword. We will also cover one of the most powerful OOPS concept, that is polymorphism. Then we will see how to work with parameterized classes. And finally, we will wrap up with encapsulation and abstraction, which are the two key concepts in the object-oriented design. So System Verilog introduces an object-oriented class data type. It is a user-defined type that bundles together data and subroutines, means functions and tasks that can operate on that data. In System Verilog, especially in verification, almost everything revolves around classes. They allow us to describe a group of objects that can share a common behavior. The variables inside a class are known as class properties, and the functions and tasks which are defined inside the class, they are known as methods. So this is a basic example of a class in System Verilog. The class is named packet and it defines three properties: payload, destination, and priority. Payload is an 8-bit field and it represents the actual data being sent. Destination, it is a 32-bit address which specifies where the data is going. Priority is a 5-bit field which indicates the priority level of the packet. So all these three are the class properties, and every object created from this class will have its own copy of all these three properties. Now let's look at the code. Class definition starts with the class keyword followed by the class name, and it ends with the end class keyword. Inside this, we declare the properties like regular variables. So these declarations define the structure of every packet object which we create. This is another example to extend our understanding of classes. In this example, the class is named circle and it defines a property called radius, which stores the radius of the circle, and two methods, or we can say two functions, that operate on this property. So the first is area. It returns the area of the function, area of the circle, using formula pi r square. And the second function is circumference. Circumference, it returns the circle circumference using the formula 2 pi r. So both of these functions are declared inside the class and they use the property radius. So I hope it is clear now how class properties and methods work hand in hand. So we have explored about classes, but how do we actually use them? Let's talk about objects. In System Verilog, an object is simply an instance of a class. It is a real working copy of class. And one powerful feature of classes is that they allow dynamic creation and manipulation of objects, means they can be created, they can be deleted or exist at runtime. And this is done using object handles. Also, please note that when you define a class, it doesn't use any memory. It doesn't take any memory. Only when you actually create an object from the class, the memory gets allocated. And this allocation is done using new operator, which creates the object and returns a reference, that is pointer to the newly allocated memory. So whenever you use the new keyword, you are dynamically creating an object and getting back its handle to work with. Let's now look at how to actually create an object from a class. So we are taking example of the same class packet which contains three data members: payload, destination and priority. So to creating an object of this class, we are following a two-step process. First, we are declaring an object handle, and then using the new keyword, we are instantiating the object and allocating memory for it. So inside the initial block, first we are declaring a class handle, that is pkth. At this point, no object exists. Then we are using the statement packet handle equals to new. So it actually creates the object and assign its reference to the handle. So that's how we create an object in System Verilog. First we declare the handle and then use the new to allocate memory. We have seen how to create a single object. Now let's look at how we can create multiple objects of a class. So we are again using the same packet class example. Inside the initial block, we declare two object handles, packet handle 1 and packet handle 2. Then we use the new operator for both the handles. This creates two separate objects, each with its own memory space for payload, destination and priority. So as shown in the diagram also, packet handle 1 points to one packet object and packet handle 2 points to another. So this is how we can create multiple independent instances of the same class in System Verilog. So let's talk about constructors in System Verilog. Constructor is a special method used to initialize an object when it is created. In System Verilog, the constructor is always named new and it is defined like a function. If we don't explicitly define it, System Verilog automatically provides a default constructor which sets class members to their default values. But if needed, we can also define our own custom constructor by writing a new function inside a class. Also, this constructor method does not have any return type, but it implicitly returns a handle to the object being created. So in our earlier packet class example, we have used the default constructor to create object. Also, one important thing to be noted here is that System Verilog does not support constructor overloading. So you can define only one new function per class. So this is an example of how to use a custom constructor in System Verilog. Let's take the packet class again with three data members: payload, destination and priority. Now notice the constructor function which is written using the function new syntax. These are the arguments for the constructor and we have added the default values for all the three arguments. So payload is defaulted to 8-bit hexadecimal value 0 and destination default value is 32-bit hexadecimal 0 and for priority field default value is 5-bit decimal 0. This way, even if the object is created without passing any arguments, in that case, these default values will be used. Inside the constructor, we simply assign the input values to the class properties. Now there is a display method that prints out the packet details using $display. So this is an example of how constructors can be customized and how their default values can be used while object creation. So in the previous slide, we learned how to write a custom constructor. Now let's discuss how to create objects using this constructor. So let's take an example of the test bench module written for verification. Inside this module, we are creating two objects, P1 and P2. For P1, we are passing the custom values to the constructor function. But in case of P2, we are not passing any arguments. Means it would use the default values which we defined when we wrote the custom constructor. Next, we are calling the display method on both packet objects. On the right side, you can see the simulation output. Packet 1 is showing the custom values which we passed during its object creation, and in packet 2 it is showing the default values as expected. So we can either override the default values as we did in case of packet 1, or we can rely on the constructor for using default values during object creation as in the case of packet 2. The next topic is null object handle. In system Verilog, when we declare an object but don't initialize it using new, the handle is set to null by default. So if handle is null, and if we try to access any property or method using this null handle, it would result in a runtime error. So we need to always check for null before using it. Let's take this example. Here we have declared a packet object P, but we are not initializing it. So we are checking if P equals to null. If it is true, then we are displaying an error message and then initializing it using new. So once it is initialized, we can safely access its properties and its methods. So it is a good practice to always check for handle for null before accessing, as it's avoid null dereference errors which could be very difficult to debug in simulation. This keyword is used to refer to the current instance of a class, and this is useful in constructors or methods when the parameters name match the class member names. For example, in our packet class, the custom constructor which we wrote has parameters named payload, destination, and priority. But the class itself also has variables with the same names. So to avoid confusion, we use this dot payload, this dot destination, and this dot priority to indicate that we are referring to the class member here and not the local arguments. If we won't use this keyword here, then the assignment would be just from the function argument to itself, and the class members won't get updated. So remember, if there's a name clash, you have to use this keyword. Means you are talking about the class variables and not the local arguments. So now let's look at how object assignment works in system Verilog. There are two ways of object assignment: shallow copy and deep copy. In shallow copy, we are only copying the pointer, not the actual data. Means both the original handle and the copied handle, both of them are pointing to the same memory location. And if you change anything using any one handle, it would affect the other also, because both of them are pointing to the same object. Shallow copy is performed by default in system Verilog, and it is useful if you want multiple references to the same object. It is memory efficient, but it could be risky, say if you modify some shared data but you didn't mean to. So you have to be very careful when you perform object assignment. This is an example of shallow copy. So we are taking the packet class again with only one property, that is data. So we are creating two object handles, packet handle 1 and packet handle 2. Next, we are creating a new object and assigning it to packet handle 1 and setting its data value as 5. Next, we are creating second object using object handle packet handle 2 and setting its data value as 30. Now at this point, both the handles are pointing to two different objects. Next, we assign packet handle 2 equals to packet handle 1. So this is where shallow copy comes in picture. Now both handles are pointing to the same object. So when we do packet handle 2 dot data equals to 40, we are actually changing the object that both the handles are pointing to. So that's why when we display packet handle 1 dot data using $display, it would print value as 40 and not not 5, which was the original value of packet handle 1. So as shown in the diagram also, both the handles are pointing to the same memory location with value as 40. So the original object which packet handle 2 was pointing to with data value as 30, this is now lost. So let's move on to deep copy. Unlike shallow copy, deep copy creates a completely independent copy of the object, including all of its data and any nested objects. So here source handle and the destination handle both would point to different memory locations, and if you change any one handle it won't affect the other. System Verilog does not support built-in deep copy. So how do we achieve it? So there are two ways. First, by implementing a custom copy method in the class, and second, by defining a constructor that creates a new object and manually copies all its data. Deep copy is highly preferred when you need independent objects. For example, say in verification scenarios where packet data should not be shared between test benches. So this is an example of deep copy. We are again taking the packet class with only one property, that is data. Inside the class, we are defining a custom copy method. Inside this method, we are creating a new object using new and then copying the data from the current object using this statement this.data. So this custom method is called using this statement packet handle 2 equals to packet handle 1 dot copy. So when we call this statement, we get a new independent object which is assigned to packet handle 2 and its data value is same as packet handle 1. So here in the diagram also, initially both handles P1 and P2 both were pointing to different memory locations with values 5 and 30 respectively, and after copying still both are pointing to different memory locations but their data value is same. So deep copy is mainly preferred when you want to work with modified versions of an object in your test bench, but at the same time you want to preserve the original data. Now let's discuss how lifetime works for class properties and methods. Starting with properties, by default every property inside a class has automatic storage type, means each object gets its own unique copy. And these properties live as long as the object itself. So when we use new to create an object, the memory is allocated for all its properties. And when the object is no longer referenced, this memory is automatically reclaimed. Now for methods, local variables inside the methods, they are automatic by default. This means they get created and destroyed with every function call. These method variables are not tied to the object's lifetime, but rather they are tied to the lifetime of the method call. Finally, system Verilog allows properties and methods to be defined as static if we want them to share the same memory location across all instances. Next topic is static properties. This is a very important concept in system Verilog classes. Static property is a class variable that is associated with the class itself, not with any specific instance. So that means irrespective of how many objects we create from the class, there is only one copy of a static variable and that is shared by all the instances. A static property can be accessed directly using the class name and the scope resolution operator without even creating an object. Although it is possible to access it through an object, but that is not a recommended way because it might confuse anyone. They might think that it is instance specific if we access them using the instance of the class. Now the question is, why do we need static properties? So static properties are useful, say if you want to store some information that is common across all the instances. For example, say if you want to track how many objects have been created. So let's look at this example. We have taken the same packet class and it has three properties: payload, destination, and priority. There is a static variable in the class named total packets created and it is initialized to value 0. There is a custom constructor function inside this class, and inside this constructor we are incrementing this static variable every time. So this constructor would be called every time an object is created, right? So every time an object is created, the static variable is getting incremented. See, in the initial block, we have three packet objects, P1, P2, and P3. And finally, we are printing the total number of packets created using the syntax. This is class name packet, scope resolution operator, and static variable name. So this is the correct and right way to access the static properties. Now what this $display would print? It would print the value as 3 because we have created three objects, and every time an object is created in the constructor function we are incrementing the value of total packets created. And since this is static, means it is shared across all the instances. So once packet P1 is created, the value of total packet created would be 1. Next time we are creating P2, the value becomes 2, and when we create packet P3, the value becomes 3. So the $display would print the value as 3. This is another example of static properties. We have a class packet again with two variables, static variable and automatic variable. This is a constructor function, and inside this constructor we are simply incrementing both the variables. Here we are declaring three handles, and in the initial block we are first creating P1 and displaying value of ID and val, then P2 and then display both, then P3 and display. Now ID is shared. ID is static variable and is shared across all the instances. So every time new is called, it increments value as 1, 2 and 3. But val is instance specific, means it starts from 0 and is incremented by 1 only. So ID value would be printed as 1, 2 and 3, but val would be printed as 1 for each call. Now we manually assign p2.id is 7 and p2.val is 3. When we set p2.id as 7, we are actually changing the static variable. So all the objects now would see the value as 7. But p2.val is 3 means we are only updating the value of p2, not for other objects. So when we again display values using these statements, so p1.id would print value as 7 because id is shared variable, but p1.val is still 1. p2.id, it would print value as 7 and p2.val as 3 because we have modified it here. And finally, when we are printing the value of static variable using class name and scope resolution operator, it would print the final value, that is 7. This is another example of static properties. We are again using the packet class with two variables, first static variable and another automatic variable. We have defined a constructor, and inside the constructor we are incrementing both the variables. Now in the initial block, firstly we are directly assigning the value to the static variable using class name scope resolution operator. So we have set the value of the static variable to 3. So this proves that static variable exists even before object creation. Now we are displaying the value of static variable. It would print the value as 3. Next we are creating the object. We are creating the object handle and then allocating a memory to this object. Now when we are creating an object, the constructor would be called and it would increment the value of static variable and val. So the value of id would become 4 now, and when we display it using this statement, it would print value as 4. I'm finishing my session here and will be covering rest of the topics in the next session. Please feel free to connect with me over the mentioned email ID or follow me on LinkedIn to get more updates. Thank you.